So I'm going to talk a bit about object storage in FlashBlade. So why are we talking object stores? Well, as most of you probably know, most applications that are built in the cloud these days are using an object store as basically the primary place to put data, right? Whether that's S3 in AWS, Google Cloud Storage, Azure's blobs, right? Cloud native applications use object stores as essentially primary storage. And that allows you to separate simple objects from rich metadata, right, where we can now keep complex schemas around, say, if I'm tracking a video database, I've got all kinds of extra information, and I can have a simple pointer off to this object that I can go grab. And so that's the way a lot of our new applications are being built. And our belief is that that's going to come more and more to applications spanning a huge range, right? And that impacts things like performance. So traditionally, on-prem or enterprise object stores were known as cheap and deep, right? There's not a ton of performance that's coming from your legacy object store. Now, some of the cloud object stores have changed that a bit, at least in the throughput department, where you can get pretty good throughput from an object store in the cloud, but you don't get that great a latency. So our belief is that as more and more applications move to object store as a fundamental interface, you're going to see a demand for high-performance object stores, both in large streaming accesses. So if you're training a neural network and you've got, in some cases, upwards of a petabyte of training data and an array of high-end GPUs to keep those fed, you need enormous amounts of throughput. But you're also going to see small random accesses that are much more latency or are really IOPS sensitive at scale. Right, so if you've got time series data coming from sensors, you've got log data that's coming in, to write those down persistently, it often becomes very latency sensitive. And so our belief is you're going to see more and more spectrum of performance demands that's going to look a lot like what you see from existing file systems today. And so this somewhat blending of the requirements of file and object leads us to ask the question, well, why would we want to stand up a whole separate infrastructure? If we're a customer, why would we put a whole separate infrastructure for object that's disjoint from a file system? We're going to end up stranding capacity, adding extra complexity, dealing with different failure requirements and scaling behavior. Why can't we just have one system that can do both? And so that's kind of the backdrop of why we're looking at an object store. And so as we think about that, how could we add an object store to FlashBlade? One of the simple ways you can think about it is let's just layer it on top of a file system. And in many ways, this is how most existing object stores are implemented. They map objects, whether they're the bucket, the container of objects, and the objects that go inside of it. You can map it to directories and files on a traditional file system. But the problem with that is that as you get to millions and billions of objects, the file system interaction becomes a bottleneck, and that's physics. That's going to be any file system, no matter how fast. Right? As you want to look up a range of objects and do the sort of metadata accesses, if you've got millions and billions of objects, you're going to have a problem. And so what everybody basically does is you put an index to solve that. Right? So we keep an internal index to track that metadata for our objects. And so we could certainly do that in FlashBlade. We could run an object index. We could run it inside, as part of the control logic. But that then becomes a thing we have to make highly available. It has to be redundant. It has to scale in performance. And it's just yet another piece of software and state to manage. And so we made the observation that, well, we basically already built one of those. It's how Purity works both in FlashArray and FlashBlade. So you can say it's objects all the way down. Right? So whether that's sections of a block or some LUN, or their inodes, files, extents in a file system, we take those logical constructs and we have a series of mapping layers that we go through. Right? So we're going from this logical namespace to an intermediate namespace and down to the physical tier on Flash and NVRAM. And so at each point of there, we're maintaining those mappings, and that's how we do compression, that's how we do dedupe in FlashArray, that's how we get really efficient layout and resiliency on Flash. And so we already have this system that allows us to create these mappings and manage them. That's essentially the same infrastructure you'd need to build an index and implement an efficient object store. So why don't we just do that? And that's really, in some ways, all there is to it. So let's walk through how we actually would serve an I/O from an object store. So I'm going to use similar diagrams to what Rob used earlier, where we have these blades with logical control and these partitions, and then our storage tier underneath of that. And so we're going to walk through the life of a read, or in object parlance, a get operation. And so if a client issues a get to bucket A of, hey, let's read object foo, then we're going to land that on one of the blades. We hash that connection and land on one of the blades. And at that point, we have to extract, okay, it's bucket A, object foo. The next thing we're going to do is we're going to then translate bucket A into an internal ID. And we're distributing that or you're hashing that across the system, just like we do with directories, with file inodes, and so forth. And so we're going to go get that bucket ID, get it back, and then we're going to, again, translate the object name, object foo, into its internal ID from the authority that controls that bucket. And once we have that, we now have all the information, the meta information to go get the data for object foo. And so we'll forward that read request now on to this object authority. And so then the final piece here is we're going to now go read the data, and I'm showing a simple case where it's already persistent on flash, but we may also be reading it from a look-aside in NVRAM. So we're going to read that object data from flash and then forward it directly back to this protocol endpoint we talked about that's holding that connection back to the client. And so there we're going to decompress and form the actual client response. And so that's it. That's the life of a get operation in our object store implementation. And so there's really two takeaways I want to leave you with. The first is this: it's kind of a two-phase operation. You may have seen, right? We do this a couple of round trips to find this metadata, and then once we know where the data is, we can now go access that. And at first glance seems kind of chatty. Like, why add this extra latency? Well, it turns out we can cache all of that, right? And so if you have any locality, we're gonna avoid those lookups. But the other main point that I'd want to leave you with is realize this is basically what NFS does, right? In a distributed file system like NFS, the client is now responsible for making those metadata accesses. When a user space application says, I want to open and read this file, there's a whole series of back and forths back to the client network to essentially do this first phase to find the file handle, and then a read operation is issued.
So the logical object ID hashes to a partition, and then the partition has its own directory structure or metadata to say, this is where the data for that object lies?
Yeah, so the question was, as we hash this object ID down to a partition, and then does that partition have its own internal sort of structure of where the data is? And yes, that's correct. And it's basically the same, at that point, it's the same machinery as how we map files, or extensive files even, right? How do we identify where that is? There's internal bookkeeping that's essentially part of that internal key value database of how we manage all these it's that mapping picture that I showed a few slides back.
And as the chassis increase and stuff like that, that mapping distributes across those.
Yep. And so as we scale, right, to multiple chassis, then we're extending those mappings. It's a global database essentially across all the blades.
So with objects, you could have very large objects being written or read, and you want to make that change atomic. Does the size of an object not have an impact on your ability to process it in any way because of that?
So the question is, if we have really large objects, right, does the size of that object have any impact on our ability to process it, especially if we're, say, creating a new version, if we have, because objects are fundamentally immutable. So no, right? The same mechanisms that we use in a file system to create atomicity around directory rename operations and moves. These are highly distributed, can be massive scale. We've had to create all of that infrastructure already to support a file system and to support very large files as well, and how we distribute all of that data and access to get efficiency. And so we're just reusing all of that here.
So can an object span a partition?
So yes, a very large object, just like we do with a very large file, we'll actually break it up and have it span partitions to help us create scale, all managed internally by our sort of object metadata database. Say that 3 times fast. All right. So as with Rob, we got a quick quick screenshot. So that's kind of the basic idea of how it works. Let's take a quick look at where we are. And so we're in advanced beta right now with this. So we've got a quick video showing. So this is a synthetic workload showing we're hitting about 6.5 gigabytes a second read and 1.5 gigabytes a second write. We were constrained to one of these old single chassis systems, so we don't have quite the eye-popping numbers that Rob had. This is also non-reducible data, right? As you find in many cases with, say, movies and images, right? They're pre-compressed. And so we're sustaining, for that kind of workload, for that kind of data, we're sustaining quite a high concurrent access through the native object store. And that's essentially because we're reusing all that same machinery that we built for the file system to achieve that high performance. There's no additional layer to kind of get in the way.
Is it all S3 or do you support Swift?
So at the moment it's S3 compatible, but again, that's kind of just that intermediate layer, and so we're looking at others. Other questions? All right. So I told you something that was true, which is that Purity is objects all the way down, but it's not the whole truth, right? It's really a key value database, and it's really a transactional key value database for exactly these reasons of, we have to create all these mappings and creating these indexes that are essentially, a key value store, but it has to be transactional to support immutable objects, to support large, atomic renames. And so this is, kind of the core foundation of everything we've built at Pure in terms of a data path. And so what allowed us to do, all the sophisticated things with blocks and in FlashArray, and now what we're doing with file and now object in FlashBlade. So if this really powerful underlying abstraction, what are we doing next? I can't tell you, sorry. But we can talk about, but we can talk about how we think about new interfaces and where they're going to come from. And so I want to share some really early prototypes that we've been building that are really focused more on the application tier of, where's the world going and where should storage support that, right? And so let's have a little bit of fun, right, and enter the world of deep learning. So I don't know how many of you have seen some of what's possible around deep learning. It's pretty incredible, right? There's not many times as a systems engineering person that you get to go, wow, I didn't know you could do that. And so I'll play this as a video clip. I'll show in a minute. But what we did was we hooked up a simple camera, just a couple $100 HD camera, to a GPU box that's running TensorFlow. That's got a deep neural network that's capable of identifying both objects by type as well as the location in the image where they're found. And it runs what's particularly cool about this model, and we didn't develop it. There's some really brilliant people at University of Washington that put this together. But it runs in real time on a consumer GPU. And so the way, as storage people, the way we think about this is you've now got the ability to take raw pixels, the ultimate kind of unstructured data, and translate that into structured information. And so we're starting to think about what does that mean for us as we build out data pipelines. And so we'll play this so you see, it's pretty neat. It's not perfect, right? Chairs will come and go. So this is identifying a chair and a keyboard, and our highly paid professional models come in and it tracks people. So we've got, the basic. So this model is trained on about 100 common objects that you see. There's another version of this same concept that has about 9,000 objects that is capable of recognizing different breeds of dogs. I mean, it's incredible what this stuff can do, and it's all running in real time. And so you start thinking about it, and it'll pick up additional people as they move, and it's really not perfect, but it's pretty awesome, right? So aside from being great technology, why are we talking about this here? Right? So, well, what do you do with it, right? So if you've got one camera, you don't need a FlashBlade, right? That's about a megabyte per second. You don't need a high-end storage system for that. But what about 50 cameras, or 100 cameras, or 1,000 or 10,000 cameras? That's actually not outside the realm of what companies are deploying now. Because you have the ability to actually derive insights from all that data, it starts to make sense, and I'm going to get loud here, it starts to make sense to deploy a large number of these cameras. So you see things like Amazon.com in the bookstore side of the house, are doing real-time inventory detection through cameras. They talked about the reInvent, how it with these deep learning models. In fact, they capture so many images in that system that they had to put a server room in the back of the fulfillment center because they couldn't get a pipe big enough to AWS. Right? So this stuff is real. It's here available now, and companies are starting to deploy real systems around it. And so,
Did you say Amazon actually does on-premises IT?
yeah, actually they said it. So there's a video where we can, yep. Think about that. So what happens, right? As I mentioned, these deep learning models, aside from being really cool visuals, they're translating raw pixels into structured data, and now we can apply all the tools we know around how to manage, a flow of structured data. So we've got, whether it's like Apache Kafka for stream management, Elasticsearch, Spark, Hadoop, all of the tools that we know from sort of the structured and semi-structured analytics world, we can apply to this. And so as you start looking at, well, what does it take to build and deploy that from an infrastructure perspective? It's an enormous amount of and varied equipment, right? So you've got, if you're running Kafka, that's its own set of servers with storage. And if you're running Hadoop, that's its own HDFS cluster. And Elasticsearch is yet another storage cluster. FlashBlade is already being used today to host a lot of those applications just through NFS, right? It's really efficient to be able to run all these clustered storage products on top of a FlashBlade, so you don't get this cluster fatigue of having to set up all these things. The compute is external, right? But they're just simple VMs at that point. And so this is, a direction that we're starting to think about. Where else can we go to help customers make it easier to deploy these complex and rich data pipelines, whether it's using, these sophisticated deep learning tools, thousands of cameras that are writing at gigabytes a second, and then the back-end analytics that come from that. We want to simplify all of that. And the question we're asking is, wouldn't it be incredible if a storage array could help facilitate these deployments of these pipelines? So that's just, some of how we're thinking about the future and where we're, thinking about going next. Make sense? A little different?
Are you going to have native hooks into TensorFlow or other ML type platforms?
Sorry.
Are you going to have native hooks into TensorFlow or other ML platforms, Cloud ML?
So the question was, are we going to have native hooks into TensorFlow or Cloud ML? Today, so we're just at the beginning of kind of exploring this. What's great about tools like TensorFlow is these, the ability of GPUs to scale in performance on the compute side creates this demand for a huge fire hose of data. And so in TensorFlow, for example, there's already a lot of facilities to pipeline data from storage, right? To make sure that those GPUs that you have racks and racks of are always fed, right? And so FlashBlade is, and we've, Park kind of alluded to this, we have a major customer that's deployed a massive scale of these NVIDIA GPUs and a whole bunch of FlashBlade now to keep them fed, right? Because the actual expensive resource is the people that are doing the experiments. And so all the rest of that is just, making sure that it's fully occupied.
And is this part here going to be announced tomorrow, or is this?
So we're talking about this as a technology preview, and so we're going to talk about it a little bit tomorrow and an expanded deep dive on Wednesday. And there's actually a live interactive, so this TensorFlow demo thing, we've got live running out on the expo floor for those of you here. Can come and check it out. So what we'll talk about on Wednesday is that you get this pipeline, and it's great, but basically we've got a gigabyte per second of data coming in over here, and a relatively small, right? We basically reduced the data down in a way to think about it. So we partnered with Google, and we can actually stream this telemetry back up to Google Cloud, right? And think about this in sort of the context of edge computing, right? You have massive density of data that's being generated by these cameras. You can't, just like Amazon.com found out, you can't buy a pipe back big enough back to the cloud. And so you reduce that data down and ship it. And so we partnered with Google to do, again, this technology showcase where we're using some of their cloud ML features for training these models, but also to do a lot of the streaming analytics. So we use the Google Pub Sub, and we could have done it on any number of things, but it's a great showcase of sort of the best of breed technologies they've got, and kind of this use case around what a lot of people are calling edge computing. So that's what we're going to talk about in much more depth in a couple of days. But it's been fun to build that and see where things are going.
So Chris and Howard Howard's question where you were saying, yes, we have S3 capability today. Do you also have GCS capability, but we just don't talk about it?
So not today, not yet. That's, we work with all the cloud vendors, or we're trying to work with all the cloud vendors, so we haven't done anything yet native with GCS, but again, that's kind of a very thin tier, and you can sort of see where we're likely to go.
In that demo that you had, the data from the camera was being fed to FlashBlade, and then FlashBlade was feeding the TensorFlow logic, or was the data going directly to TensorFlow then to FlashBlade?
Both. So the question is, are we feeding the data to FlashBlade and then to TensorFlow, or is it straight to Tensor? It's really to both, right? And so we have a small piece of software that kind of tees that stream, so that we want to write down the raw sensor data as quickly as possible, because we're thinking about, downstream, if there's a failure of some software component, we can actually go back and replay, because the processing is all deterministic as long as we capture that original source data.
Display overlay is being generated by TensorFlow and fed back to this. So
actually, the overlay is done in the browser. It's a D3 JavaScript in the browser. What the TensorFlow model gives you is coordinates and a label. Right, so it's really structured information. And that's what's cool about it, because now you can feed it to all these other analytics pipelines.
Actually an object, one object for the camera stream at that time? Or?
So no, each frame is being treated as an object. Yeah, so it's a little bit inefficient on the browser side, but we're not really in the business of making very efficient client-side browser demos yet.
This is what we see. We see this massive change in applications. We see them moving much more to these parallel architectures and parallel in ways that we haven't seen it before. It's not true of the older applications being revisioned, but it's certainly true of the new applications being deployed today. We see algorithms changing almost weekly. I mean, TensorFlow is kind of the flavor of the moment, but there's lots of other things happening at the same time. And we're seeing this notion of having lots of data that you can derive some insights from is incredibly valuable. And not just hoarding it, but actually learning something from it, doing something with it. Being able to go back in time with a new learn model and ask, hey, I found out there was something new I should ask about. Let me go and ask that question against history. And that's kind of what Brian is going to demo really is. It's not just being able to put boxes around things here and now, but also going to say, hey, I'm going to train a new model, and I'm going to ask against history. Where has this model been in the past? That changes how you think about things. And the more you integrate that deep down, the more you create value. We talk a lot about this in engineering. Massively parallel is the new normal. It's just the new normal. It's not the way you build a classical ERP system, but it's certainly how you build a new class of application. And frequently that leads into this dialogue, and it's a dialogue that I think is important. It's like, how do I take that and make it compatible with what I got? My answer is, I don't think you do. I think of this way. In the 80s, we got this revolution. We started really, truly digitizing the business record, the business process. And that's just not changing. We build control systems, and that's kind of the world we've been in for the last 40 years. This whole new fourth revolution around the AI and big data, it's about the physical world. It's about things that aren't a business process, about things we can touch. This is why we see these in places like farming. This is why we see these in places like healthcare and manufacturing, in cars and transportation. This is the industry touching the real world. This doesn't go away. This is not supposed to suggest that we're replacing this from that. No, they can run in parallel with each other, but they're touching two very different aspects of industry. And this, I think, is really changing really, really fast. And I don't think it will touch this. I think it will be completely independent of and move it in a different direction. FlashBlade participates a bit in both. But we think quite a bit about this because we've been driven in there by lots of our early customers. They're taking us to places we've never been before. And they're thinking about problems that are really fantastic and unique, problems that we just didn't think about in that sense over the last couple of years. And so when we give you the hints on kind of what we're thinking around with TensorFlow, we're thinking about processing, deriving structure of the non-structure, and sort of forking that I/O layer, and sort of letting cloud functions interact with it. We think about that very, very differently because this world didn't exist before. It's not an incremental make it better. It's a massive leap forward. So anyway, that's where we are. Hope you kind of enjoyed it. The world is just about to change. It's going to be great. Thank you.